Hi, so we're up to the last section in Chapter 2, Section 9, Combined and Joint Variation. And there's a couple new terms that we're starting out with at the beginning, but then other than that, it's really just taking what you've already done and applying it to now where we'll have three or more variables. So the first thing is terminology, and want to define combined variation and joint variation. If you think back to the types of variation we had before, we had direct variation and inverse variation. So combined variation is really just a combination of those two. So combined variation, I'm going to say it contains both direct and inverse variation. And as far as what that means, if you think back to direct variation, that was always y equals k times a variable. So if it has to have direct variation, it's going to have an aspect of that to it. So I'm going to write y equals k times x. But then that has to also have the inverse variation, which is where we had a variable in the denominator. So you could say, maybe let's put a z in the denominator. So here would be an example of y varying directly with x and inversely with z. Maybe for a more generic formula, we'd have to say a variable equals k, and then to have both, you'd have to have at least one variable in the top. So I'm going to say variable and put the little s in parentheses. So k times one variable, or maybe multiple variables up there. But then also in our denominator, we also have to have one or more variables there. So I'm going to write the variables with the s in the denominator as well. So that's combined variation. The other option, then, the joint variation, has to be either all direct or all inverse, because we already did the combination. And direct variation actually is going to be just all direct variation. And you could try to think of like a joint in the body. You can extend a bone, like your elbow joint, and make something long and skinny. That's kind of what you get when you have the joint variation. This here is two or more. So joint variation equals two or more direct variations. And to write that out, it has to be, well, I'll skip the y's, but y equals k times x times z, or something like that. You have to have at least two variables with the k. So maybe I'll say, for my example, let's just do the generic and say a variable, often y, but not necessarily, equals k times a variable times the second one. I'm going to write variables with the possible s, variable, put the s in parentheses. So we have to have at least a variable equals k times, and there has to be at least two variables there. Could be more. Now for the very last part of Chapter 2, and it's looking at finding k when we have three or more variables. And it's really the same sort of thing as what we did before. Before, when we had like y equals k times x squared, we had to have an x, we had to have a y, and then we could solve for k. Now the same sort of thing is true, but we need to have all the variables except for k like before, but that's going to be three or more variables. And you may need to pause the video and copy some of this down, or you really could just write the equation and maybe say Roman numeral 2, finding k, write the equation, then jump right into the example. But I'm referring back to the sheet that we had in the notes from section 8. So I wrote in the last section, Francine found an equation for pressure as a function of depth and the density. And there's the equation that we pulled out of the notes yesterday, section 8. So like before, to find k, we need to put in numbers for everything but k in the equation and then solve for k. So if I move down to my next page, and I'm maybe going to write out the equation again. So we have p equals k times capital D times lowercase d squared. And we're looking for k. So really we could use any of these points here for the capital D, because density was the capital D and capital P was the pressure. So those don't really matter. None of them look insanely wonderful, so I'm maybe just going to go with the first one. So D, then I'll put 0.5 for my capital D, putting it in parentheses just to kind of separate it from everything else. There's nothing special about that. But then I have 15.6 as my pressure, equals K. Now at first look we're kind of stuck because we don't have everything we need to solve for K. And a lot of times K is going to be sandwiched up here in the writing because they did a controlled experiment that you only can change one variable at a time, your manipulated variable, and then see how the responding variable responds. So the other variable has to be controlled. And if we go right here, we see that when we were doing the density changes, the depth was always 25 inches. So we could take that 25 inches and put that in there. So now we have everything except for K, so we could go through and solve for it. I'm going to grab my trusty calculator, and I'm going to simplify that right-hand side. So I have 0.5 times 25 squared. That gives me 312.5. So 15.6 equals K times 312.5. And now it's just going back to math that you've been doing for years. So divide both sides by 312.5. Divide both sides by 312.5. Those cancel. And so 15.6. If I had a variable that was, or a number that was really nasty with a lot of decimals, I'd make sure to use my answer key so I didn't round. But I come up with a K being 0.04992. So K then equals 0.04992. And once you find K, we always put it back in the equation. So capital P equals 0.04992 times a capital D for density times a lowercase d for depth squared. And now we have an equation that would work. So from here you'd be able to go on and put in different density values, depth values, and find the pressure. And that rounds out all the notes for Chapter 2.